Welcome. In today's video we're going to be looking at geometric sequences. So to begin with, let us first define what a geometric sequence is. So a geometric sequence is a sequence of numbers such that the ratio between consecutive terms is constant. So let's go through a few examples of what this might be. So for example, if we look at the series of numbers 3, 6, 12, 24, you'll notice that the ratio from 3 to 6, or going from 3 to 6, you see that we double. And then going from 6 to 12, we also double. And then going from 12 to 24, we also double. And so we say that the geometric sequence has a common ratio of 2. In other words, each time we move up one term in the sequence, we multiply by 2. Equally, we could look at the sequence 1, a half, a quarter, 1/8, and you'll notice each time we move a successive term or up a term in the sequence, we actually halve the term before. So we go from 1 to a half to a quarter to an eighth. So then we would say that the common ratio is in fact 1/2 because we halve it every time. And so here we would say this is an increasing geometric sequence. This is a decreasing geometric sequence. And the final one we're going to look at is a little bit more peculiar, but if we have a look at this geometric sequence here, where it goes 4 to -8 to 16 to -32. And what you'll notice here is that from going from 4 to -8, we actually multiply by -2. Going from -8 to 16, again we multiply by -2. And then 16 to -32, again you've noticed we multiply by -2. And so this is, again, we would say a common ratio of -2. And we'd say that this would be an alternating sequence of numbers. So let's formalize this a little bit with some notation. So we're going to say Tn is the nth term in the sequence, and let R denote the ratio between consecutive terms. And we're going to say A is the first term in the sequence. So what we'd have is that obviously the first term is A, as defined here. The second term in the sequence is A multiplied by R. So the first term is A, then we multiply by the common ratio R to get the next term. To get term 3, again we have to multiply by R again, so this gives us AR squared. And continuing on, so forth, we've got also T4 is AR cubed one more time. And in general, what we're going to notice here is this pattern here. We've got the nth term in the sequence is the initial term A multiplied by R to the power of n minus 1. So for example, let's just take T4. You'll notice here we've got an n of 4, and here we've got a power of 3, which is equal to 4 minus 1. So let's go through an example now. The first term of a geometric sequence is 2, and the fourth term is 54. Find the sixth term and the common ratio. That would be 1. And then in example 2, or part 2 of example 1, the fourth term of a geometric sequence is -250, and the seventh term is 31,250. Find the first term and the common ratio of the sequence. Alright, let's go back to example 1 here. So, in example 1, what we had is that the first term of the geometric sequence is 2, and the fourth term is 54. And so what we're going to write this as is T1 equals 2 and T4 equals 54. And again, if we let Tn have this form AR to the n, then we get two simultaneous equations from these two results above. The first result says T1 is 2, which means A is 2. The second result, because T4 is 54, that tells us that AR cubed is 54. So, One way we could solve for r is by substituting this value of a equals 2 into the second equation, and by doing that we get 2 times r cubed is 54. Divide both sides by 2 gives us r cubed is 27, and then of course taking the cube root of both sides gives us r equals 3. And this is the common ratio we were looking for. And now we have to find the sixth term, and to find the sixth term we simply need to plug a equals 2, r equals 3, and n equals 6 into this equation above, and that's exactly what we've done here down the bottom. 2 times 3 to the power of 6 minus 1, which is 486. In example 2, we're going to see that the fourth term of the geometric sequence is negative 250, and the seventh term was 31,250. And so using these two pieces of information, we can write T4 is equal to negative 250, and T7 is equal to 31,250. From here, again, what we're going to do is we're going to label Tn is equal to AR to the n minus 1. And so we're going to replace T4 with AR cubed, and we're going to replace T7 with AR6 in these two equations. And this gives us equation 8 and equation 9. So one way we might be able to solve for these two equations, you notice here that there's a factor of a and a factor of a. So my first instinct to solve these equations simultaneously, to do it through, there's two ways. Again, when we remember how to do simultaneous equations, there are two ways to approach this. There's either the elimination method or the substitution method. In this case, I'm going to use the elimination method, but not by subtracting the equations from one another. In fact, I'm going to be dividing the equations by one another. So you see, if I divide the left-hand side of equation 9 by the left-hand side of equation 8, the a's will cancel out, and therefore I'll only be left with r's, and that'll be very useful. And that's exactly what I'm going to do. So, if we do divide equation 9 by equation 8, on one side of the equation we get AR to the power of 6 over AR to the power of 3, which then simplifies down to R cubed, and then we get 31250 divided by negative 250 over here, which gives us negative 125. And then solving this equation gives us actually R is equal to negative 5 by taking the cube root. Then what we can do is we can substitute this equation, equation number 10, or the fact that R is equal to negative 5, into the first equation. So it gives us A times negative 5 to the power of 3 is negative 250, which gives us A is equal to 2.